In today's class, we are going to consider some questions and answers on atmospheric physics. And the first question says, what is electromagnetic spectrum? Before I go straight to this answer, I would like us to take a look at a clearer picture of what the electromagnetic spectrum is all about. Looking at this figure, you will see the order of arrangement of electromagnetic waves and their frequencies and wavelength. So by my left here, you see the frequency in hertz, and by the right, the wavelength. If I scroll down, you will now see that the frequency is inversely proportional to the wavelength. Looking at here, you have a higher frequency, while at this other point, you have a lower wavelength. So frequency is inversely proportional to wavelength, and we have the arrangement here. We have the radio wave. After the radio wave is the microwave. After the microwave is the infrared. After the infrared, we have the visible light. You see the colored region here is talking about where you have the visible light. And immediately after the visible light is the ultraviolet ray from the sun, and then we have the X-ray and the gamma ray. So this is simply the order of arrangement of electromagnetic waves. The order of arrangement of electromagnetic wave according to their wavelength and frequencies. Okay, so let's look at the way we can define them, or other ways we can define the electromagnetic spectrum. So electromagnetic spectrum is the continuous spectrum of electromagnetic radiation. Electromagnetic spectrum is the continuous spectrum of electromagnetic radiation. It covers an enormous frequency range. So the frequency range could be, or is between 1 Hertz to 10 to power 25 Hertz and all of that. We can also define it this way. Electromagnetic spectrum is the range of all possible frequencies of electromagnetic radiation. The range of all possible frequencies of electromagnetic radiation. Another way we can define the electromagnetic spectrum is the third definition here, the range of wavelength or frequencies over which electromagnetic radiation extends. So whichever one you are comfortable with, you can define it that way. The next question says, electromagnetic spectrum is made up of two broad components. What are they? The components include the long wavelength and the short wavelength. If we go back to the figure here, you can see that by my left we have frequency and by my right we have the wavelength. So when the wavelength is longer, it has weaker penetration. So this region you have the radio wave, the microwave, and the higher you go, you have a shorter wavelength, and those ones tend to be stronger. So the components are subdivided into two. We have the long wavelength and the short wavelength. So the longer wavelength have a lower penetrating power than those ones that have shorter wavelengths. Name the components and the parts in each component in order of increasing frequency. Name the components and the parts in each component in order of increasing frequencies. Let's still go back to the figure. Order of increasing frequency. Look at the frequency. You can see that if we are talking about order of increasing frequency, looking at the index here, 10 to power 3, and then 10 to power 4, 10 to power 5, 10 to power 6, 7, you now see that the frequency is increasing. So if you are asked to list the members of the electromagnetic spectrum in order of increasing frequency, you have to start from the radio wave, the microwave, the infrared, the visible light, the ultraviolet ray, the X-ray, and the gamma ray. That order is an order of increasing frequency. Remember, when frequency increases, wavelength decreases. So if we are also considering order of decreasing wavelength, is the same thing as increasing frequency. If you look at here, we have 1 kilometer in terms of the wavelength, 1 meter, 1 centimeter, 1 millimeter, 1 micrometer, 1 nanometer, 1 picometer. You see that the wavelength is decreasing in this case. So if you are asked to write the members of the electromagnetic spectrum in order of increasing frequency and order of decreasing wavelength, they mean the same thing. If you are asked to write the member of the electromagnetic spectrum in order of decreasing frequency, it means you will start from gamma ray, X-ray, UV ray, visible light, infrared, microwave, and radio wave. Or if you are asked to write the members of electromagnetic spectrum in order of increasing wavelength, then you have to start from the gamma ray, the X-ray. It means the same thing as decreasing frequency. So with the table, we should be able to attempt the question below. This one says, name the components and parts of each component in order of increasing frequencies. Okay, so the first component we written here, the long wavelength. Long wavelength in order of increasing frequency, we have the radio wave, the microwave, the infrared. On the other side of the component, the short wavelength, we have visible light, ultraviolet light, X-ray, and gamma ray. The next question says, what would the equivalent in order of decreasing wavelength be? What would be the equivalent in order of decreasing wavelength? So I have already explained this, that when we talk about decreasing wavelength, it's just the same order: radio wave, microwave, and all of that. Okay, so it's still the same thing as what we have written here. The radio wave, microwave, infrared, visible light, UV ray, X-ray, and gamma ray. The next question. It is convenient for practical purpose to divide the entire atmospheric regime into two parts. How is this feasible? it is convenient for practical purpose to divide the entire atmospheric regime into two parts. How is this feasible? Okay, so we have that this is made feasible because of the wide difference in temperature between the Sun and the Earth. The next question says, name the two parts of the atmospheric regime. Name the two parts of the atmospheric regime. So the two parts include the solar and the terrestrial. When we talk about the solar, we are talking about the short wavelength. When we talk about the terrestrial, we are talking about the infrared or the longer wavelength. Okay. The next question says, can frost formation take place in temperate region? Can frost formation take place in temperate region? When we talk about temperate region, it's simply the region of the globe where we have the latitude 40 degrees to 60 degrees north and south of the equator. So the question is if frost formation can take place in this region of the earth or the globe. The solution, yes, it can. And the reason is that frost formation can take place under very dry air and very dry sky. So the air has to be very dry and the sky has to be clear. The air has to be dry and the sky has to be clear. Please, if you have not yet subscribed to this channel, I would like you to do us a favor. I would really appreciate you. I want you to click on the subscribe button. Thank you very much. Let's now go to the next question. This one says, briefly explain why a car parked under the sun is hotter than the ambient temperature. Of course, this is an example on greenhouse. So you now see that the light from the sun is more of a short wavelength. The UV ray is transparent to the windscreen of the vehicle but is opaque to infrared. So you now see that if it does not have the re-radiated infrared does not have space for it to escape into the atmosphere, will tend to trap more heat and the windscreen of that vehicle behave more as greenhouse gases. So we have here that the gases of or the glasses of the vehicle behave like greenhouse gases. It is transparent to solar radiation and it is opaque to infrared. The solar radiation could be in the form of the UV ray. It has a shorter wavelength and can or could penetrate into the glass. But when it re-radiates where you have the seat of the vehicle, it becomes infrared heating effect, and at that point the glasses become opaque to infrared. The blocked infrared is partly radiated out while part is re-radiated back into the vehicle, causing the heating of the vehicle more than it would be outside. So that's the solution to that question. This one says, what is temperature inversion? Temperature inversion. Solution. Temperature inversion is referred to a condition in which temperature profile of a place is reversed from normal. You now see that most Before now, we used to say that the higher you go, the cooler it becomes. The higher you go in altitude, the cooler it becomes. But it's not like that in our atmosphere. At a certain point, you now see that temperature, instead of becoming cooler, tend to increase as you go higher. That's what we mean by temperature inversion. Temperature inversion refers to a condition in which the temperature profile of a place is reversed. Can temperature inversion occur in the tropics? Yes, it can. It occurs everywhere. So it can occur in the tropics as well. This one says, under what condition temperature inversion can occur at night, clear sky, or in dry air? So those are the conditions where temperature inversion can occur. Occur at night, occur in a clear sky, and dry air. The next question says, natural greenhouse effect is not desirable by man. Natural greenhouse effect is not desirable by man. Is this statement true, and why? Natural greenhouse effect is not desirable by man. Is this statement true, and why? We know what they mean by greenhouse effect. So it is by the help of greenhouse effect that makes our planet to sustain life. Without that, our planet would have been very cold. So this statement is not true. This statement is not true because without greenhouse effect, the temperature of the earth would have been very low, lower than it would have been, and would not have supported life. Okay, so let's move on here. This one says, write down equations used in calculating the total energy of a gray body and a black body. Write down equations. So we are not to calculate, we are just to write the equations. And the gray body has the equation, the total energy E equals to epsilon sigma T to the power 4. We also have, for the black body, that's the expression. So the symbol here represents emissivity factor. And the next symbol represents the Stefan's Boltzmann constant. And the last one represents absolute temperature. The next question says, explain the Earth energy budget and list any two of its importance. Explain the Earth energy budget and list any two of its importance. So we have that the energy budget describes the balance between the incoming radiant energy that reaches the Earth from the Sun and the energy that returns back into space. So the amount of energy that comes into the Earth, irradiates, and returns back into space is given account by the energy budget. The Earth energy budget describes the balance between the incoming radiant energy and that which returns back into space. Okay. And the second question says, why is it important? If you look at here, we see explain the Earth's energy budget and list any two of its importance. But we are going to list even up to 3. Whichever one you prefer, you can pick. So it's gives understanding of changes around us. So the energy budget gives an understanding of the changes around us. It gives a clearer picture of regional distribution of energy across the globe. And the next point here is that it helps us to observe its impact on weather and ocean circulation. Please, I would like you to do us a favor by clicking on the subscribe button if you have not done that. And if you have done that, I still appreciate you. Thank you very much. The next question here says, what is radiative forcing? Radiative forcing is a measure of the influence a factor has in altering the balance of the incoming and the outgoing energy budget. A measure of the influence a factor has in altering the balance of the incoming and the outgoing energy budget in the atmospheric system. You can as well define it as the change in energy flux in the atmosphere, the change in energy flux in the atmosphere, which is caused either by natural or anthropogenic factors. The change in energy flux in the atmosphere caused by natural or anthropogenic factors. Looking at this diagram here, you can see the Earth's energy budget, and it gives account of the amount of incoming energy and the outgoing energy. But in this case, you can see that the picture is showing us a positive radiative forcing, because if you look at the figure here, looking at the figure here, you now see that the incoming short wavelength, the incoming short wavelength here, the energy coming into the Earth is about 343 watts per meter square. You now see, look at it very well. Now, most of them are being absorbed by the cloud. Some of them have been absorbed, about 20% has been absorbed by the cloud, and 48% has been absorbed by aerosol and other greenhouse gases. 169% have been absorbed by the surface. So the amount that has re-radiated back into space is about 21%, 69%, and then 16%. So the figure here is more of, how do I put it? You have a positive radiative forcing. Have a positive radiative forcing here, because in this globe here, in this of the Earth, we tend to increase because the amount of energy returning back into space is not the same as what was absorbed. Okay, so that's just the figure is for us to really understand it well. The question was, what is radiative forcing? It's the change in energy flux in the atmosphere, which could be caused by natural or anthropogenic factors. The next question says, list the gases which can initiate a positive radiative forcing. List gases which can initiate positive radiative forcing. We may have positive radiative forcing. We may have negative radiative forcing. The we may have a positive radiative forcing if the global temperature tends to increase. We may have negative radiative forcing if the temperature tends to decrease. There are gases which are responsible for positive radiative forcing. We've listed the following. So a positive radiative forcing is produced by raising the concentration of greenhouses. Raising the concentration of greenhouses. Here we have CO2, CH4, N2O, and the F gases. When we talk about the F gases, we are considering the hydrofluorocarbons. This is the acronym. The perfluorocarbons. The acronym is here. Sulfur hexafluoride, HF6. Nitrogen trifluoride, NF3, which in turn warms the planet, while the negative radiative forcing leads to cooling of the Earth's surface by the release of airborne particles or aerosol. The next question here says, can ozone layer depletion cause global warming? Can ozone layer depletion cause global warming? When we talk about ozone layer, it is a protective gaseous envelope that protects the planet from harmful UV rays that come from the sun. But when we talk about depletion, we are referring to eating up of this protective layer of the atmosphere. So the question now is, can it lead to global warming? Yes, it can. Explain your answer. Can ozone layer depletion cause global warming? Yes, it can. Ozone layer depletion allows more solar radiation in the form of UV region to reach the Earth's surface, thereby increasing the amount of infrared radiation which is re-radiated, leading to more counter radiation, which is a primary cause of global warming. So ozone layer depletion allows more UV ray to penetrate, and then it re-radiates in the form of infrared, and it is this infrared that we mean by the heating effect. Of course, this heating effect is being trapped by the greenhouse gases, which leads to global warming. So ozone layer depletion can as well lead to global warming. Name any other effect of ozone depletion. Effect of ozone depletion on human. The sunburn. It could also lead to skin cancer, sunburn, skin cancer, and all of that. Please, thank you for watching our channel. Thank you for watching our video. This is Supreme Online Lectures. I really appreciate your time and your stay. I want you to do us a favor by clicking on the subscription button if you have not done that. Have a wonderful day. Bye.